Hello, and welcome to this video of the A-Level Maths Explained series. I'm Diego, a doctoral candidate at the School of Mathematical Sciences at Queen Mary, University of London. And in this video, we're going to see an example of how trigonometry is fundamental in our daily lives. And indeed, it has been for a while. As of 2020, 84% of UK adult population owned a smartphone, devoting to it 2 hours and 34 minutes on average every day. Usually, in these smartphones, we will have an app allowing us to use a GPS service. GPS stands for Global Positioning System, a radio navigation system operated by the United States Space Force, which started as a military project and nowadays has 31 satellites in orbit around Earth. We use it when we want to cycle or drive somewhere where we have never been to, or when we want to find the shortest route to our destination. However, how does our device find our location so precisely, within a few seconds of opening the app, and sometimes when we are not even using it? As surprising as it might seem, the mathematical principles on which the system is based are very simple, and we can gain a good understanding of it only with basic trigonometry. First, let's assume we live in a two-dimensional world, that is, in a plane, just like the main character in the popular novel Flatland by Edwin Abbott. And let's see how our GPS would work in such a world. Then, it will be easier for us to understand how the actual GPS works in our three-dimensional reality. So imagine we turn our GPS receiver, usually our phone or car navigator. And how does this device find our location in our two-dimensional world? Well, the process is called two-dimensional trilateration. Our device will start receiving signals from the different satellites around Earth, forming the GPS network, informing of the distance between each satellite and the GPS receiver. So, if we start receiving signal from satellite A, and we know the radius of the Earth, small r, the radius from the center of the Earth of the orbit of the satellite A, capital R sub A, and the angle alpha sub A formed between the straight lines from the center of the Earth to the satellite and from the center of the Earth to the GPS receiver, then we would have exactly 3 pieces of information of a triangle, right? 2 sides and the angle contained in them. From what we know of trigonometry, this determines uniquely our triangle, and it's enough for us to compute the other 2 angles and the length d sub a of the third side of the triangle. But what is that third side? Precisely the distance between our GPS receiver and satellite A. Does anyone recall which of the trigonometric formulas we know would allow us to compute distance d sub a? Exactly, the cosine rule. That is, d squared equals r squared plus capital R sub a squared minus 2 small r times capital R sub a times the cosine of alpha sub a. Is this enough for our GPS receiver to find our location? No, because all of what our device knows so far is that the distance between satellite A and itself is d. And so a priori, we could be anywhere in the circle with center, the satellite, and radius d sub a. At this point, the receiver will get another signal from satellite B and perform the same calculations using the cosine rule, obtaining that way d sub b, the distance between the GPS receiver and satellite B. And once again, we can see normally this would not be enough to find our precise location, since the intersection of 2 circles in the plane could be 2 different points. So we need to catch the signal of a third satellite C, from which we would be able to compute d sub c, giving us a single intersection of the 3 circles and thus finding our location unequivocally. So far so good. But all this is happening in a two-dimensional world, where everything is simpler than in our three-dimensional reality. So how does the actual GPS work in 3 dimensions? Well, as you could guess, the process here is called three-dimensional trilateration, and it is essentially the same process we described for 2 dimensions. Which are the differences? Well, here the distances we compute, d sub a, d sub b, and d sub c, will define spheres with center the satellite instead of circles. And so, having 3 of these distances won't be enough to define a single point. Since the intersection of 2 of these spheres, for example, the ones defined by d sub a and d sub b, will be a circle, its intersection with d sub c will still give us 2 possible locations, and so we will need the signal of a fourth satellite d to compute the distance d sub d, defining our location uniquely. A quick search on the internet will show dozens of websites describing beautiful applications of trigonometry, including more details on how the global positioning system works. I hope you enjoyed the video and that it helped you appreciate how mathematics we all learned at the school are widely used in tools and devices we use in our daily lives. Our lives are more and more dependent on technology as time goes by, and understanding elementary mathematics is becoming a need to perform many tasks successfully in a fast-changing world. Thank you for watching.